Hey, Christian, you made it.
Yeah. Oh, yeah. Thinking. Roads are fine now.
The what?
The roads are fine now.
Yeah, actually, the main roads are okay.
Yeah, the one getting to my house is a little, but I'm on it for a second. So.
Okay. Golden, then?
Okay, please.
I cannot read. That's fine.
If we all the way went through the same circle, you'd be able to not have to walk over here to do the somewhere.
In principle, yes, but now that you've moved the classroom, I think that'll be confusing to a certain extent, right?
Right.
Because first of all, the whole idea was to it's not bad. If you go by that, what you're teaching one student then I would say it is not at all bad. Yeah. It's inconvenient, but it's okay. That's the way I would say. It's like weather. I mean, yeah, it's inconvenient, but it's not bad that you can really do it. Yeah. So that's the way I would put it. So it's okay. Yeah, that's not. Okay, so I have to change these directions. Have you guys started the homework? How is it going?
Pretty good so far.
Tell it again. I think I missed.
It's been pretty all right so far. I've just
Pretty
been
all
working on the
right.
first part, the first
Good.
question.
Okay. So it's, and the last one is in a sense, if you start from the expression, then you got to build on it. Yeah. So I think, again, hopefully that's not too bad. Okay. So I met someone on my way here. Oh, come on. Oh, shoot. What's happening? Okay. I was telling that I met someone on my way in the student center, and that took away 2 minutes. So I'm delayed by 2 minutes. So how much time? Okay, hopefully this is better. Okay, better. Okay. Yeah, there's a homework. Homework 3, correct? We postponed it to February 15, Monday. And there is a midterm coming up next week. And did we say anything about midterm? How is it going to be or anything like that? Nothing yet, right? Yeah, so you'll have it during the period, or what do you say, between the class times. And I'm wondering whether to make it take home or not. Yeah, let me decide by Monday or Wednesday. I do it 2 ways. I think, Jeremy, you're the only one who has not taken it before, right? Or maybe Wahid also. So last semester, what I've done is that sometimes I make it is an hour-long exam during the time period, but I release the exam, you do it in your own way, and then you submit it, upload it within the time period. And the second possibility is that I make it take home. So that means that it is available 1 day before, and it is due by, let's say, in 24 hours or something. So it's like pretty much like a homework, but a little more time constrained in the sense it is a day or two instead of a week long. So I'm not sure exactly what I want to do at this point. Most probably, like, I don't mind the take home part because this is the second part of the course. I've done the assessment in the first part, I guess. But I'll see. I'm not sure about it. Yeah, I'll decide by next week. Okay, so yeah, we talked about a straight a wire magnetic field, and or actually we did the vector potential due to a straight wire, and we took that reasonably to detail until the last moment where we took the limit. The same thing can be done for the magnetic field also, but I won't go through the details. I'll keep the infinite wire in mind. And at least the finite part, you have seen that before in some introductory level physics. So the finite part, magnetic field is easier to do. you don't have to substitute sine hyperbolic theta. It is instead you substitute tangent theta. So maybe, yeah, here is where, so we need a quiz, right? So quiz is calculate B for a finite length of wire. So basically derive, so there is a formula for the magnetic field due to, so what is the magnetic field due to a finite stretch of wire? So this is, let's say, some length L. And if you were to make an observation point here, if it was infinitely long, we know that it is phi hat times mu naught over 4 pi times 2 times I over the radius rho, right? That's the formula if you have infinitely long wire. If you make it finite, the correction is reasonably straightforward as far as you know what this theta 1 and theta 2 is. So there is an expression like this for a straight line. And this angle theta 1 and theta 2 is the projection down here. So this is theta 1, and that's theta 2. Okay. So find out what happens when theta 1, how it goes to the limit of a straight infinitely long wire, and basically derive this. Right? Again, this is typically available in introductory level physics, or even if we do whatever we did, it's just instead of sine hyperbolic function that we substituted, you have to substitute a tangent function. And I think that's reasonable to ask. Is the question clear? Right. Okay. Okay. So the straight wire is done. So let's try to go beyond that. So let's have a circular wire. So this is circular. Wire. And let's say this is the circular wire carrying a current I. And let's say the axis of this circular wire is along the z-axis. And this is, let's say, the radius A of the wire. So that's your radius A of the wire. And what else do I need to specify? And we will have an observation point somewhere. So let's say that's your observation point R. Like that's a geometry of what we would like to analyze. We know that the vector potential due to a source, due to a current distribution, is given in terms of current density. So let me write that down. So it's mu naught over 4 pi, and add up all the contribution from individual currents, right? The currents here are on a circular loop, and add up all these quantities. And yeah, so that's R minus R prime. What is the current? To begin with, we need to have a current density formula. So what is the current density? It's just a matter of decoding where this current density is. It is on a, let us say it is at z equal to 0 plane, and it is at a radius or the cylindrical coordinate radius rho equal to a, right? What's the direction to begin with? It's in the circular direction. If your cylindrical coordinate, that's phi hat. But we are in primed coordinates, so it's phi prime hat. Unlike the rectangular coordinates, these change with angles. So this is whether it is prime or prime unprimed, they are different coordinates, and especially when they are under integration. So we have to be careful not to switch from one to the other. Right? So that's one thing, and we have current I, but current density is current per unit area. So we need two length coordinates in the denominator. That means there will be two delta functions in a sense. And one of them is delta of z minus 0, let's say. And the second piece is that radius rho is equal to a. If there is any confusion as to is this really a correct, so maybe we are missing something, you should immediately calculate a small constructed area here, right? Think of an area here, and that area should capture your it should capture the complete current I going through it. And if you say this is the phi equal to 0 plane, so let's quickly do this. Phi equal to 0 plane is the area. So dA dotted with J, right? So this is, I'm integrating on this whole half plane, right? Rho equal to 0, so I should get the total current in that case. But area, what is the perpendicular direction to that area? That's a phi hat itself. So that's equal to rho and z, right? So you integrate over rho, 0 to infinity. Let's say this is primed, so that's rho prime. Infinity is minus infinity to plus infinity dz prime. And what's the direction? That's the direction is phi prime itself. And the current dotted with the current, so that's dotted with phi prime hat time a times delta of z prime times delta of rho prime minus a. Oh, this should be z prime and rho prime. Sorry about that, because I'm in the primed coordinates. All the sources are in the primed coordinates. So this should be z prime, and that should be rho prime. That was a mistake. This is equal to 1, and once that is equal to 1, delta functions can be immediately done. So that's indeed equal to I. Right? So that's correct. Right? So the current density that we wrote down seems to represent the correct quantity that we need. So with that, let's proceed. So I'm going to erase this. That was just a check. Now it turns out that we need to do a little warm-up exercise here. If we do this for an arbitrary point r, it turns out that this expression is very difficult to calculate. Okay, and we are going to come back and do this using a certain function that we will introduce. But for now, let's make it simple. Let's put the observation point all the way onto the axis. Okay, so this is a very special exercise. So let R be on, like, in fact, let's make it simpler, right? First of all, it can be on the axis. Then there is a special point on the axis that is right at the origin. So let's make it even simpler. Let's make it on the origin. So let R be at the center, right? At the center of the wire, right? Very special approximation, but nevertheless, we do know that there will be a magnetic field there, right? What will be the magnetic field there based on your introductory physics? What's the magnetic field at the center of the wire? The expression for that? Mu naught I. So answer to this is B, not even A, right? So this is magnetic field at the center of the wire. It will be in the z direction. Okay, that's because you hold the wire, and all the contribution will come from there. And there will be mu naught over 4 pi, that's because of the SI units. Then what? There will be current, right, divided by, remember for infinite wire, what was it? So mu naught over 4 pi 2I over rho, right? And that's in the phi hat direction. This was the magnetic field due to an infinite wire, right? And it is in the circular direction of the, it circles the wire. What is it for a wire at the center of the wire? And you study this because it is only at the center. You won't talk about it anywhere else because it's hard to present in undergraduate physics. But at the center, you do talk about it. And it looks very similar to this, right? Except that some numbers change. So instead of 2 pi, so you instead of 2 there, you have 2 pi, right? And instead of a rho, how far are you? This is A, right? You're fixed length, so that's A. Right? So that's a formula. Typically, you don't write it in this form because you're consistently in SI unit there. So you would say this is 2 times A. And this one, you typically say this is mu naught I over 2 pi. There is an expression even we can calculate on the axis, and that's what we'll do. But we are going to do the vector potential, and there'll be a catch in this whole thing. Right? So, any questions at this stage? So we are aiming for this, and then we will switch. Right? We'll make an approximation, or at least for one approximation, we will get a nice result. But the complete result, we will do it without approximation. Okay, so at the center, it should be easy, right? Because vector R is straightforward, correct? Help. Yeah. What is R? Yeah, so what is happening at the center? At the center, R is equal to 0, correct? So there's an immediate simplification there. So let's do it here. So A, am I still in the, yeah. And now I'm at 0, right, at the origin. That's equal to mu naught over 4 pi d cube r prime and j of r prime is equal, divided by r is 0, so it is just r prime. But the magnitude of r prime is simple. It's just the vector, it's the length a, correct? So the whole, this distance comes out. Correct? So that makes it simpler slightly. So right, so that's equal to mu naught over 4 pi 1 over a. And this is d cubed, so let's say this is minus infinity to plus infinity dz prime, 0 to infinity rho prime, d rho prime, d phi prime, 0 to 2 pi. Right. And then we have phi prime I. So that is I here, I can pull it out. Let me write it here if you want. So it's phi prime I and delta of z prime and delta of rho prime minus a. Correct. Phi prime, notice, does not depend on z prime and rho prime. Phi prime, it's good to see this. If you have a rectangular coordinate system, that's your, let's say, rho, vector rho. but that's rho hat, let's say, of unit length. Correct. This is of length rho, and there is an angle phi associated with it. What's the direction of phi hat? That will be tangent to this. So that's your phi hat, which is the same as I can move that vector along. So that's your phi hat. Right? If you want, this is rho prime, and that's prime, right? If you're in the primed coordinate, so it's a prime coordinate. If that is phi prime, this is angle phi prime. So in that sense, you can motivate that rho prime is actually a unit vector. So it is cosine of phi prime, because like make a right triangle here, use right triangle geometry, right? That's cosine phi prime I hat plus sine phi prime j hat. Right? Just giving you an explicit version. And if that is the case, phi prime hat has make the geometry opposite, right? It's in the second quadrant. Since it's in the second quadrant, the x component has to be negative, but it's the opposite like here, right? So it is minus sine phi prime I hat plus cosine phi prime j hat. Various ways of looking at it geometrically. You can do it also by saying that change in rho prime is in the direction of the tangent of a circle. So either way, but that's your phi prime. But notice it does not depend on z prime and rho prime. So this integral is independent. So I can do these two integral immediately, the delta function integrals. So this is equal to mu naught over 4 pi. Remember, delta function integrals are simple. Just replace wherever z prime comes, if it appears anywhere, to 0. And wherever rho prime appears, I have to set it to a. Like that's how I evaluate my delta function integrals. And there is an I here. I take out that I. Rho prime gets replaced with a. So that's here a. And rest of them just collapse, right? So this integral is gone. This integral is gone now. And whatever is remaining is 0 to 2 pi d phi prime and vector phi prime. So a cancels out, and we are left out with an integral of a tangent vector, right? Remember that, how does this look like? You have a circle, and phi prime is somewhere here, right? So that's your phi prime, and that's your vector phi prime hat. Right? That's a tangent to the circle. If I were to add up all the tangents to the circle, all over the circle, vectorially, what do I get? Right? You should get a 0, right? Because there, for every vector here, there is another vector in the opposite direction, right? So this is like this, like this, like this. So if you add up all these vectors, geometrically, you know that that's going to be 0. Algebraically also, you can see that phi prime is sine phi prime plus cosine phi prime. If I were to integrate 0 to 2 pi of sine phi prime, it is 0 because it's going from 0 to 2 pi. Right? It is a periodic function. If I were to plot sine phi, this is a positive area, that's a negative area, 0 to 2 pi, it'll go away. So that's 0, right? So that's exactly 0. So that's simple. So the magnetic vector potential at the center of the circle is 0. Is that correct? Right? So if that is correct, then one can argue the following. So the magnetic field at the center is equal to curl of the vector potential. All right. So vector potential is 0, so the magnetic field is 0, but we said it was not 0, right? What's wrong in the argument that I just now said? So my point is that, or I'm arguing, and I'm saying it is wrong, is that vector potential is 0 at the center of the circle. So the curl of the vector potential, this is 0, curl of that is 0. So the magnetic field will be 0. So magnetic field is 0 right at the center. But I gave you an expression for that in the introductory level books that we give. So what's wrong in that argument?
Whenever you integrate flat hat prime changes with d phi prime as you go through the.
Yeah, but that I took care, right? That's our integral. How about this? I'll give you a hint. This is correct. Vector A is 0 at the center. But the magnetic field is not apparently according to introductory level physics books, which I think is probably correct too. So how can both be right? Either one of them must be wrong, right? You would say, I mean, of course, this is the thing that you're not familiar with. You would suspect this. But I say this is correct. So how do you put it together with B is equal to del cross A? Curl of a vector potential, how can it be non-zero if the vector potential is 0? Is it even possible? You do come across such a thing before in mechanics. So let me put it in a simpler way. Maybe the curl is confusing. Yes. Moment? No. Maybe. Okay. Here. How about this? Acceleration is derivative of velocity. If I have velocity equal to 0, then what is, so if I say velocity is equal to 0 at a point, what's the acceleration at that point? At that point is 0, right? Sure. So let's say I throw a ball up in the air, right? The velocity of the ball right at the top, what is that? 0. What is its acceleration? Right, it's negative 9.8. It better be, because that's what we calculate, right? So what happened to this formula then? Yeah, you can add a constant, but it will go to 0 anyway, right? What happened to our derivative of velocity? If velocity is 0 right on the top of the trajectory, why is the acceleration not 0? Right? Yeah, I can raise this as well. Yeah. So we go up, right? So right here, velocity is 0. So acceleration is dv by dt. Why is it not 0? It's because derivative cannot be talked in terms of one point. Derivative involves 2 points, right? So this is equal to v of t plus delta t, how much ever small, minus of v of t divided by delta t, right? In the limit delta t tends to 0. It doesn't matter whether you take limit or not. For calculating the acceleration, I need the next point, how much ever close it is. And right adjacent to that, it is not 0. How much ever close you go, it is not 0. And that ratio turns out to be exactly 9.8. Exact. Is that clear? Right? Did I clarify that clearly? Okay, so very close to that. Like if you were to zoom it in, there is a point here. The very next one is not 0. So the slope of that, I mean, its slope, this is going in a straight line, yeah, with respect to time, its slope is not 0. So something can be non-zero even if the function, not the function is 0. Just knowing the function at one point is not sufficient to calculate its derivative. We need to know, have more information, right? So the curl of A cannot be calculated with just one point information. I need to have another point. I need to have a distribution around A0, what happens if I want to calculate the magnetic field. So electric potential at just one point doesn't help me at all. Like I need to know either along a line or along the surface in principle if I want the complete magnetic field. Is that clear, the argument? Right? So this is not good enough. But let's do one more. But maybe we can do the magnetic field using our, since you cannot do it this way, let's proceed and get it using our Biot-Savart law, right? So at least, because I did not do that for a straight wire, maybe I should do that here, right? So do the same thing. Now, let's do B directly, right? Since, but at the origin now, okay? I cannot do it everywhere because it's too complicated, right? And we will, I'll describe that for you later. Okay. Magnetic field, what's the formula? So it is mu naught over 4 pi times dqr prime times J. Right? And this is the quiz that I gave you. You have to do this for a infinite or a straight wire, finite straight wire. I'm doing it for a circular wire. This is, oh, sorry, that's not the expression, right? That's J. So Biot-Savart law says that this is J of R prime crossed with R minus R prime divided by R minus R prime cube. Right, that's our formula for the magnetic field. Again, we are interested only in 0, so this is gone, right? That's gone too. So that's a simplification that comes about. And R prime then is 0. So R prime, magnitude of R prime is equal to A. And what is R prime itself? This will be, this is along the circle, right? So this will be vector A times rho prime hat. Is that clear? Right? If you're on the circle, it is A times the vector rho prime wherever it is. So if I were to draw this, right, that's your rho prime, right, and that's your phi prime. And this length is A. Is that clear? Any questions? So we can also write, if you want, this as A times cosine of phi prime in the I hat direction plus A times sine of phi prime in the j hat direction, right? That's also, we can write that. So it seems like it's very scary because, oh, last time we got this integral over phi prime hat and it went to 0, right? So what if it happens again? What's the integral of rho prime? That's also 0, right? Everywhere this is circular, so it will be 0. But let's see what happens. Right, so this is equal to mu naught over 4 pi times, this is R prime equal to A. So I can pull that out completely. So that's 1 over A cube. And then we have d cube R prime, J of R prime. Should I write that explicitly? Why not? Yeah. So this is equal to I, let me write this slowly. How about that? J of r prime crossed with rho hat, right? Minus a, so it's a minus a times rho hat. Is that clear? So just substituted because we are on the center, at the center of the wire. So that's equal to minus mu naught over 4 pi 1 over a square. And let's do the integral now, right? So this is 0 to infinity or minus infinity to plus infinity dz prime, 0 to infinity rho prime d rho prime, and we have 0 to 2 pi d phi prime, and what else? There is a I delta of z prime delta of rho prime minus a, and there is an I, no, I have already, and a phi prime hat crossed with rho prime hat. What's the cross product of phi prime hat and rho prime hat? Cross product. 1, but it's a vector, right? Try again. Minus z hat, right? So we have rho prime hat, phi prime hat, right? Phi prime minus cross rho, it will be to the inside, so that's minus z hat, correct? Which is nice because we have our answer. We earlier said the answer is in z hat, right? So that's minus z hat. Is that clear? Any questions on that? It is z prime hat, but z prime and z hat are the same, right? At every point, it doesn't matter where you are. Prime and as far as the unit vector goes, it is the same, not the coordinate itself. Right? So suddenly we don't have to worry about everything because otherwise everything was going to 0, right? Z prime doesn't go to 0, they all add up, right? So this negative sign and this negative sign comes up together. So we have z hat mu naught over 4 pi 1 over a square. And the z prime and rho prime integral can be done immediately. That one of the rho prime gets a times I, and there is still an integral remaining, that's 0 to 2 pi. And if you were doing elementary ways of doing Biot-Savart law, you would have almost written this right away, right? You would have said, oh, there is a current contribution from this point at here, so that's here di, and there is a contribution at the center, which is a distance I apart, and there is an equal contribution from all over, so it is d phi integral, and you would have directly written that formula, right? So that's a 2 pi there, and probably I can write one more line, I guess. So that's equal to z hat times mu naught over 4 pi times 2 pi I over a. Again, you can cancel these two and write it as 2a, and that's what you would have done. Okay. Any questions at this stage? There is one immediate extension one can make. I did it at the center. I can do it on the axis, correct? So that's one immediate thing that happens. And again, if you do it for a vector potential, that comes out to be 0. Everywhere on the axis, this will again be 0. And can we see this right away here in our expression? Let's see. right? So we were doing this if I had not set this to be on the origin, if I were on the axis, then I will have a z here, right? Z minus, so the distance would be r minus, so this will be my r, right? That's your r. And my r minus r prime would be this quantity here, which would be z square plus a square, right? So r minus r prime on the axis would be z square plus a square. Agreed? So I can replace this quantity with z prime over a square, and I'm good, right? This will be z square plus a square, and everything else goes through. Agreed? Again, I'll reach here. This will be z square over a square, but this integral is 0 anyway.
Camera up.
Up, sorry. Sorry. So I was saying that I think you guys missed that. So here there was an a, right? Earlier, in the earlier expression, there was an a here, but this time I have a z square. I replace that a with z square plus a square, like r minus r prime. So earlier r, when I was at the origin, this was equal to a, and now r minus r prime is actually equal to z square plus a square. But it doesn't change with the angle. Every point has the same contribution, so it again comes out of the integral. It just stays as z square plus a square. That's the only difference. But eventually, this integral will again go to 0, and that's equal to 0. Is that clear? Any questions there? So A is 0, I can again cannot calculate the magnetic field using this formula unless I try to get the z component, because derivative in z is possible, right? There are 2 points there. But it's 0 everywhere, so it's going to be 0 anyway. So it won't help me, right? But what about the magnetic field using, like we can again do this here, right? So again, we set this to 0, but this time let's be careful. Like, let us see what's the direction in there. So let's be a little more smarter here. And I'll try to do this right on top of this itself. R minus R prime now, like I argued. So we are on the axis now. This is z square plus a square. Agreed? On the axis of the wire. For every point on the source, it is z square plus a square. So this is the figure. Here on the diagram, doesn't matter which point of the circle, it will always be, this is z, that's your a. So that's your r minus r prime. Like that, z square plus a square. So that comes out the same. So this still goes out of the integral. But now your r minus r prime, what is the vector r minus r prime? That's equal to vector r is in the along the z axis. So that's z in the k hat direction minus r prime is still in the plane. So it is a times rho prime hat. Is that very clear? Any questions at that stage? Can I proceed? Yeah, question. Yeah, z hat actually, yeah, or z, oh, sorry, z, no, z, yeah, z times z hat, yeah. K hat or z hat, like I was avoiding the z prime so that z times z prime or z hat, it might be confusing, but that's okay. Yeah, okay. Well, let me proceed 2 steps further. Let's do this, right? And the only difference now is, so this doesn't come out minus right away. So this is 1 over a cube. And you have, instead of rho prime here, you have this whole z times z hat. Notice it's z, not z prime, minus of a rho prime. So this is still a cube. And let me get rid of that plus. And I have rho prime minus a. And I have j is rho phi prime hat, right? Crossed with z times z hat minus a times rho prime. So the only extra piece is this here, right? This was already there. This is the only extra piece. This whole thing remains the same. But the extra piece that we have, what does that contribute? This is phi. My battery is running low. Okay, we'll manage it within the next. So phi prime crossed with z hat. What is that equal to? And z prime is the same as z hat, remember. Phi prime. So think of the circle here. That's rho. And that's your phi prime or phi hat crossed with z, right? Right. So that will be rho prime. So this is equal to rho prime. But then you're integrating over the whole of your phi. So what is integral of d phi prime of rho hat prime? That will be 0 because this is going all the way from 0 to 2 pi, right? Vectorially, they're all pointing in all directions. So that's again 0. So this term does not contribute. So the only difference is that the denominator, instead of a cube, it is z square plus a cube. So we go back to our expression earlier. So this is a jump I'm making. That's mu naught over 4 pi. Instead of a cube, this will be z square plus a square. A cube is 3 by 2. And the earlier we get 2 pi times a, right? And in the z hat direction. And I, right? That is I also. Okay. I jumped the step, but you should be, I'll encourage you guys to fill that in. I might ask this in the exam, like this is a reasonably good thing to ask in the exam. You're expected to be aware of this. I have not completely done it in the class, so I'll sort of require that in the exam, something like that. Okay. Any questions on that? And I'll stop here, I guess. I crossed 2 minutes. Next time we will actually do this arbitrary place, but then we will make the radius of the sphere very small. And that will be very neat solution there. And after that, we will keep this very general. And that will be very ugly, but we will have to introduce a new function for that. We will introduce what is called elliptic functions and get to write the answer in terms of what is called elliptic functions. Okay, thank you.
See you.
My battery is dying. So Christian, did you make progress on that? Did you try